everyone, this is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I'm going to discuss about the problems related to the operational amplifier. So in that, the problems related to the comparator and inverting and non-inverting operational amplifiers. So here the first problem is related to the op-amp comparator here. So generally the op-amp comparator or any comparator, the function of that one is to compare the applied input signal with the given reference signal. So depends upon the input signal is greater or lesser compared to the reference voltage, we will get the positive saturation level or negative saturation level across the output of the operational amplifier. So here I can take one op-amp comparator, the minus plus inverting and non-inverting terminals. So suppose if I am giving the input to the inverting terminal and the reference signal to the non-inverting terminal, so that it is the inverting comparator. So always the inverting and non-inverting operational amplifiers are, we can differentiate by input signal to where we are applying here, whether we are applying to the inverting terminal or to the non-inverting terminal. If we are applying the input signal to the inverting terminal, so that it is the inverting operational amplifier. If we are applying the input signal to the non-inverting terminal, so that it is the non-inverting operational amplifier. So in applications, whether we are utilizing the inverting operational amplifier or non-inverting operational amplifier, so those belongs to the inverting comparator or non-inverting comparator. That may be in any applications. So in this particular case, so here we'll apply plus VCC as well as minus VEE to the 741 operational amplifier. So in this particular inverting comparator, whenever my applied input signal is less than the reference voltage. See here, the input voltage is the negative value and the reference voltage is the positive value. So this negative value is less than the positive value. So positive value, why I am calling it as positive value means it is connected to the non-inverting terminal. So in this particular case, my output I can get it as positive saturation level. Why? Because positive voltage only higher than the negative voltage. That is nothing but reference voltage is higher than the applied input signal. And in the next case, if I am applying my input signal is greater than the reference voltage. So in this case, my negative signal is greater than the positive signal. So that's why my output voltage goes to the negative saturation level or negative saturation voltage. So in this way, depends upon the applied voltage, you will get the signal as positive saturation level or negative saturation level in the case of comparator. So the same concept will be applicable for the non-inverting comparator also. Here I have considered here it as the inverting comparator. So the same operation is applicable for the non-inverting comparator. The only difference here it is the input signal is applying to the non-inverting terminal and the reference signal is applied to the inverting terminal in the case of non-inverting comparator operational amplifier. So for this problem, this concept is required. So that's why I revised this concept. So next we'll move with the problem. So while coming to our first problem, design a comparator circuit for input voltage equal to 2 volts peak to peak. That is nothing but input signal or peak to peak voltage value is 2 volts. That is nothing but this is input signal. Okay. Wave at frequency 1 kilohertz. The given frequency is 1 kilohertz. And the reference voltage is given as 500 millivolts. And the resistance for the comparison is 100 ohms. And supply voltage is plus or minus 15 volts. That is nothing but plus or minus VCC value is plus or minus 15 volts. Draw the output waveform for this particular comparator. So in the given problem, they given all the parameters related to the comparator, and they given the input signal frequency as well as voltage. So we need to apply that we need to design the comparator by using this particular values, and we have to apply this given signal with desired frequency and desired input voltage. Then we have to estimate and draw the output waveform related to that applied input signal. So for that purpose, here this particular problem we can solve in two ways, by using inverting comparator or by using non-inverting comparator. So first I am considering the inverting comparator. Okay. So in the case of inverting comparator, what I said already, inverting comparator means input signal we need to apply to the inverting terminal, and the reference voltage is applied to the non-inverting terminal. Okay. And in the problem, the given plus or minus VCC value is plus or minus 15 volts. So here it is plus 15. And here it is minus 15 volts. This is nothing but plus VCC value, and this is nothing but minus VEE value. So here we'll measure our output signal. This is 741 inverting comparator. So here V reference is applied to the non-inverting terminal and input signal is applied to the inverting terminal. So in this particular case, when my input signal is less than the reference voltage. Okay, whenever the input signal is less than the reference voltage means negative value is less than the positive value. So that is nothing but what we can say, the positive value is only more. So that's why in the output I will get plus saturation, positive saturation level, that is approximately equal to the plus VCC value, that is plus 15 volts. So it will reach to the plus 15 volts whenever the input signal is less than the reference voltage. Okay. And when this is the first case, and whenever my input signal is greater than the reference voltage, that is nothing but here also it is negative value and this one is the positive value, but in this case negative value is higher than the positive value. So that's why in the output we will get it as negative saturation level or negative saturation voltage, and that is approximately equal to the minus VEE value, that is minus 15 volts here. So always in this particular inverting comparator, the output is shifting between positive saturation level to the negative saturation level, depends upon the applied input signal compared to the reference voltage. So this same concept we will apply for the waveforms. So in the given problem, the given input signal as sinusoidal signal. Okay, this is input signal. Okay, the maximum and minimum values 2 volts peak to peak means in the positive duration 1 volt and in the negative direction 1 volt. So total 2 volts peak to peak. This is given in the problem itself. And along with this, they given the reference voltage as 500 millivolts. So first I am considering the positive reference voltage. So that's why I am indicating in the positive axis that reference voltage. V reference, that is equal to 500 millivolts here. Okay, 500 millivolts. So for this input signal, what is the output we are going to get? This is varying with respect to time and this one also will vary with respect to time. The output signal. See, till here if we observe the waveform. See, from here to here, if we take the input signal from here to here, see, in this particular case, our input signal Vi is less than V reference. Okay, till here, input signal Vi is less than the V reference voltage. Okay, so whenever the input signal is less than the V reference voltage means what? What we will get? V in is less than V reference means we will get the signal value as plus V saturation, though it is the inverting comparator. So it will, till this particular duration, it will goes to plus 15 volts, that is nothing but positive saturation, and that is nothing but plus VCC. Okay, till the duration. But after this, our input signal is greater than the reference voltage. Till here, from here to here, the input signal is greater than the reference voltage. So whenever the input signal is greater than the reference voltage means negative voltage only greater than the positive voltage. So it will move to the negative saturation level. That is nothing but it will shift to the negative saturation level. That is minus 15 volts. That is nothing but minus V saturation, and that is nothing but minus V here. Okay, and after this, again our input signal is less than the reference voltage from this point onwards. So once the input signal is again less than the reference means again it will move to the positive saturation level. So that's why it is moving to the positive saturation level, and it will continue till this particular point. Why? Because till this point our input signal is less than the reference voltage V reference, and after that again the same V in is greater than the V reference, again it will move to the negative saturation level. So it will repeat for all the cycles. So this is the condition whenever the input signal is less than the V reference, and this is the condition whenever the input signal is greater than the V reference voltage. So in this way we will get the signal is shifting positive saturation level to negative saturation level in the case of inverting comparator. Okay, so this is the case when we take the reference voltage as the positive, and if we take the reference voltage as negative. So in that case, again I am taking the waveform. That is 1 volt, minus 1 volt. This is input signal, and this is, it is varying with respect to T. And for this, we will get the output signal as, and here the reference voltage I am taking here it as minus 500 millivolts. Okay, but the concept is same here in this particular case. So whenever the here input is greater than the V reference means in this case it will give it as minus V saturation, and whenever the input is less than the V reference voltage, in that case it will give it as positive saturation level, reverse to the previous case. Why? Because it is reference voltage is negative here. So in this particular case we will get the signal as first till here negative saturation level, again it will move to the positive and again to the negative. So this is these two values whenever V in is less than V reference, and this is the case when V in is greater than V reference. Sorry, I have written it as reverse, positive, negativities. Okay, in this way we will get the signal for the negative reference voltage. Okay, so this is the case whenever we consider the inverting comparator. Or else if you wanted to draw this comparison output waveform by using the non-inverting comparator, we have to consider the non-inverting comparator. For that purpose, I am taking non-inverting comparator. So in the case of non-inverting comparator, reference voltage to the inverting terminal and the input voltage to the positive terminal. And here we'll measure the output signal, and here plus 15 volts, here it is minus 15 volts here. So in this particular case, whenever the input signal is greater than the V reference voltage, we will get it as plus V saturation. Why? Because V in is fast. And whenever V input signal is less than the V reference voltage, we will get it as minus saturation level here. So this concept will be applicable for the waveforms also. So for that purpose, I am taking the same input signal, what is given in the problem, with the same frequency and peak to peak voltage. Here it is 1 volt, here it is minus 1 volt. Vin, it is varying with respect to time t. Okay, and I am taking the reference voltage as the positive voltage, V reference, that is equal to 500 millivolts. So in this case, what is the output I can expect is V naught equal to see here, whenever the input signal is less than the reference voltage, here it will goes to the negative saturation level here. That is nothing but minus 15 volts. And whenever the input signal is greater than the reference voltage till this point, so it will move to the positive saturation level, that is plus 15 volts, that is equal to minus V saturation level. Okay, and whenever the input signal is less than that one, means again it will move to the negative saturation, and next cycle it will move to the positive saturation level. So in this way it will repeat. So this one for V in is greater than V reference, and this is the case when V in is less than V reference voltage. So in this way we will get in the case of non-inverting comparator, and this signal is quite opposite to the inverting comparator signal. Why? Because the polarity is changing here. In the case of inverting comparator, output is 180 degrees phase shift with respect to the input signal. But in the non-inverting case, it will be not like that. And the same signal with the negative reference, we'll see now. Okay, this is V in 1 volt minus 1 volt. So for this, my output signal, I can expect, here it is, I am taking the reference as minus reference, that is minus 500 millivolts. So in this case, I'll get the signal as still. Here in this case, V in is greater than V reference. So it is positive value. And in this particular position, V in is less than V reference, so negative saturation. And again here it is positive saturation, and again here it is negative saturation. This one is V in is greater than V reference, and this one is V in is less than V reference. This is plus 15 volts. This is minus 15 volts. That is positive saturation, and negative saturation is depending upon the how much supply voltages we are applying for the circuit. So in this way, we have to design the comparator in order to get the square wave from the sine wave by using the comparison operation. So next we'll move to the second problem. So this second problem is purely related to the op-amp slew rate and how to find the peak-to-peak voltage and frequency of the particular signal from that particular op-amp. So while coming to the problem, an op-amp with a slew rate equal to 0.5 volts per microsecond is used as an inverting amplifier to obtain a gain of 100. The voltage gain versus frequency characteristics of the amplifier is flat up to 10 kHz. Determine the maximum peak-to-peak input signal that can be applied without any distortion to the output, and also the maximum frequency of the input signal to obtain a sine wave output of 2 volts peak-to-peak. So to solve this problem, first we will write the given parameters. The first parameter is slew rate. We can represent here it as SR is equal to 0.5 volts per microsecond. And gain, the given DC gain or voltage gain is 100. And it will constant up to frequency 10 kHz. And here in the first bit, we need to find maximum peak-to-peak voltage. Okay. How much maximum peak-to-peak voltage we need to apply this op-amp to get the output without any distortion. And the second thing is we have to find the maximum frequency required for the input signal to obtain a sine wave of 2 volts peak-to-peak. Okay, how much frequency we require to get 2 volts peak-to-peak sine wave. So we need to find these two values here. Peak-to-peak voltage as well as required input signal frequency here. And for that purpose, first of all, in the first bit I need to calculate peak-to-peak voltage. Peak-to-peak voltage is how much? So for that purpose, I am considering the formula of slew rate, that is 2 pi f V peak divided by 10 power 6 volts per microsecond. So this is the formula for slew rate here. So here we know the value of slew rate, that is given 0.5, 2 pi, frequency also given, that is 10 kHz, 10 into 10 power 3, and V peak to peak we need to calculate 10 power 6 here. So here 0.5 into 10 power 6 is equal to 2 pi into 10 into 10 power 3 into V peak to peak. So from this I can write V peak to peak value as 0.5 into 10 power 6 divided by 2 pi into 10 into 10 power 3. So after simplification, I'll get it as 15.91 volts peak to peak. So this is the first parameter we calculated. Peak to peak voltage we required here, it is 15.91 to get the without distorted output across the amplifier here. And the second parameter we need to calculate here, it is frequency. How much frequency required for the input signal. So for that purpose, again I am considering the slew rate formula only, that is 2 pi f Vp by 10 power 6 volts per microsecond. So in this case, we know the value of V peak to peak slew rate. So from this, we can find the value of desired frequency. So for that, I am substituting the slew rate value, that is 0.5. This is the formula for slew rate, is equal to 2 pi. We don't know the value of frequency. And peak to peak, just now we have calculated. Sorry, peak to peak value is given in the problem itself. In the second, in the second bit, they asked for the maximum frequency of the input signal to obtain a sine wave output of 2 volts peak. So this 2 volts peak to peak we have to consider here. Not whatever we calculated, this one we should not consider. This one They asked in the first bit, so that's why we have calculated here. But in the second bit, the given peak to peak value is different. We have to consider that one here. So that is 2 volts divided by 10 power 6. So here 0.5 into 10 power 6 equal to 2 pi into 2 into F. So F equal to 0.5 into 10 power 6 divided by 4 pi. So almost we will get it as 12.56 megahertz. So in order to get 2 volts peak to peak undistorted output across the operational amplifier, we need to provide the input signal frequency as 12.56 megahertz. So here we need to remember the formula of slew rate to find the desired frequency and desired peak to peak voltage for the given amplifier. So while coming to the next problem. So in the next problem, for a non-inverting single supply AC amplifier, input resistance Rn equal to 50 ohms, input capacitance Ci equal to 0.1 microfarad, and the coupling capacitor C1 equal to 0.1 microfarad, and the resistances R1, R2, R3 is 100 kilo ohms, and the feedback resistance is 1 mega ohm, and the supply voltage is plus VCC equal to plus 12 volts. So from this AC amplifier, we need to determine the bandwidth of the amplifier as well as maximum voltage swing of the amplifier. So this is the problem related to the AC amplifier using op-amp. Okay, this is the problem related to the AC amplifier. So first of all, we will write the given parameters. That is, input resistance is 50 ohms, input capacitance is 0.1 microfarads, C1 also 0.1 microfarads, R1, R2 and R3 are 100 kilo ohms, and the feedback resistance is 1 mega ohm, and the supply voltage is plus 12 volts. So from this we need to find the bandwidth and voltage swing. We need to calculate these two parameters for this AC amplifier. So in order to find these parameters, first of all, I have to know the circuit of AC amplifier. So that's why I'm drawing the circuit of AC amplifier here using operational amplifier. So that's why I'm taking the operational amplifier here with inverting and non-inverting terminals, and here non-inverting terminal is grounded, and for the inverting terminal we are providing the resistance R1, and here we will apply the input signal, that is Vin, okay, and the feedback elements are RF resistance and the capacitance C as well as the inductance L, and this is the load resistance R, and here we'll measure the output signal, and here it is plus VCC, that is 12 volts given in the problem itself, and here it is minus VE, it is the 741 AC amplifier. Okay. So from the given data, we can calculate the AC input resistance of the amplifier. So that is AC input resistance of amplifier is RIF. So that we can write it as R2 by R3 into RI 1 plus A. This is a formula for the input resistance. So when Ri into 1 plus A beta value is greater than R2 or R3. So in this particular case, we can simplify this one as RIF is equal to R2 by R3, that is approximately equal to 100k by 100k. Why? Because all the resistance values are given as same 100k. That is equal to 1 ohm. So the RIF value we got here it as 1 ohm. So next, the lower cutoff limit can be determined by using the formula FL is equal to 1 by 2 pi Ci of RF plus R. So this is the formula for the lower cutoff frequency. And here substitute the values. 1 by 2 pi Ci value is given as 0.1 microfarads. And the feedback resistance is 1 and the output resistance is 50 here. So 1 by 320.44 into 10 power minus 6. So it is approximately, we will get it as 3.12 kilohertz. So this is the lower cutoff frequency or lower cutoff limit. And next, the gain of the amplifier. Okay, the gain of amplifier is, I am writing here it as 1 plus RF by R1. That is the non-inverting gain equal to 1 plus 1 mega ohm divided by 100 kilo ohms. That is nothing but 1 plus 10 is equal to 11 ohms. Sorry, 11. No units for gain. Gain is 11 we got here. So from the formula of unity gain bandwidth, we can write it as unity gain bandwidth is equal to UGB is equal to gain into frequency, that is AV into upper cutoff frequency. So from this we can write FH as unity gain bandwidth divided by gain, forward gain, that is 1 mega ohm by 11. That is nothing but 90.90 kilohertz. So this is the upper cutoff frequency of the amplifier. We have calculated lower cutoff frequency and upper cutoff frequency as well as gain values. And next we need to calculate bandwidth here. So the bandwidth is equal to the difference of upper cutoff frequency and the lower cutoff frequency. Upper cutoff frequency is 90.90 kilohertz into 10 power 3 minus lower cutoff frequency is 3.12 kilohertz. So almost it is 87.78 kilohertz. This is the bandwidth. So this is the first parameter, bandwidth we have calculated. And next we need to calculate the voltage swing. So always the voltage swing of the amplifier is depends upon the how much supply voltage we are providing for the amplifier. So in this case, in the ideal operational amplifier, the maximum output voltage swing is approximately equal to the supply voltage plus VCC, and that value is 12 volts. So voltage swing is equal to plus 12 volts here. So the two parameters we have calculated here, bandwidth as well as voltage swing from the given parameters of the AC amplifier. So while coming to the next problem, in figure A, I'll give the figure. An inverting amplifier is shown with the R1 resistance 20 kilo ohms, feedback resistance 100 kilo ohms. A load of 10 kilo ohms is connected to the output with input voltage of 0.7 volts. From this, calculate I1 current, output voltage, load current as well as total current I0. So in the problem itself, they given it as inverting amplifier. So it is the problem related to the inverting operational amplifier. So in the problem, they given the circuit as So here Vin is applied and the feedback resistance RF is also there, and this is R1 and this is I1, and the same current will be flowing in the RF also, and it is grounded, and the output current I0 is flowing in this direction, and here we are having the load resistance RL V0. So it is 10 kilo ohms value minus plus 10 kilo ohms, and the load current is flowing in this direction and the output current is towards the op amp, it is flowing. So this is the circuit given in the problem itself, and the given parameters are R1 20 kilo ohms, RF 100 kilo ohms, RL 10 kilo ohms, and the input voltage is 0.7 volts. We need to calculate I1, V0, load current IL and I0. So we need to calculate these 4 parameters from the given circuit. Okay. So for that, from the given circuit, we can say this one is node A. Okay, this one is node A and this one is node B. I have already mentioned, because of the virtual ground concept, if any one of the terminal is grounded means automatically virtually the remaining terminal is also acts like a ground here. So here VA is 0 or ground means obviously VB also 0. That is nothing but there is no flow of I1 current inside the operational amplifier. So that's why the total current which is flowing through R1 and through RF to the output only, not inside the operational amplifier. So this is the important thing we need to consider while calculating any parameter in the operational amplifier. That is nothing but VA, VB both are zeros here. So to calculate the first parameter I1. So I1, how we can calculate I1 is Vin minus VB by R1 here. The drop across the resistance R1 here. That is nothing but Vin minus VB by R1. So here Vin value is Vin by R1 by because VB equal to 0 here. So Vin value is 0.7 and R1 value is 20 kilo ohms. So this is 35 microamperes. So this is the first parameter from the given problem. And next parameter we need to calculate here, it is output voltage. Though it is the closed loop operational amplifier, we need to write the output voltage in terms of the closed loop gain. So that's why V0 equal to Vin into closed loop gain ACL. So that value is, gain value is minus RF by R1 by because it is inverting amplifier. Always in the inverting amplifier the gain is minus RF by R1, and in the non-inverting amplifier the gain is 1 plus RF by R1 here. So here feedback resistance value is 100 and R1 value is 20 and the input signal value is 0.7 volts. So minus 3.5 volts the output voltage is. So here the negative sign indicates 180 the output signal is 180 degrees phase shift with the input signal because of the inverting operational amplifier. And the next parameter we need to calculate is load current IL. That is nothing but the current which is flowing through the load resistance RL. So that's why we are writing here it as V0 by RL. So V0 value just now we have calculated minus 3.5 volts and the load resistance is given as 10 kilo ohms. So it is minus 0.35 milliamperes load current. So the negative, already I have mentioned, the negative sign indicates that it flows from ground towards the output terminal. And the next parameter we need to calculate here it as the total current I0. So here as op amp input current is 0, that's why I1 is flowing through R1 as well as RF only. So that's why if we apply KCL at output node, so if you apply KCL at output node, here it is means we will get here it as the total current I0 is equal to IL plus I1. So this is the current leaving from here, that is equal to I1 current as well as IL current are entering to the node. So that's why I0 equal to IL plus I1. So I0 equal to IL plus I1. IL value is 0.35 milliamps plus I1 is 35 microamperes. So it is 0.385 milliamperes. The total current I0 is. See here, while calculating the I0, we should not consider the negative sign. Why? Because once the direction is fixing from ground towards the output, negative sign need not be considered again while calculating the output current. So that's why I0 equal to 0.385 milliamperes. So in this way, we have to calculate the parameters in the inverting operational amplifier. So while coming to the next problem, for a non-inverting amplifier shown in figure, calculate the closed loop gain ACL, output voltage V0, load current IL, and the output current I0. So first of all, I'll draw the given circuit. It is the non-inverting amplifier, so that's why in the circuit they given the input signal connected to the non-inverting terminal. Vin is equal to 0.8 volts. Okay. And the R1 value is 10 kilo ohms given. And the RF resistance is 20 kilo ohms. And the load resistance value is 2 kilo ohms. And this is node A and this is node B. And this one is grounded here. The input is connected to the non-inverting terminal, so it is the non-inverting amplifier. So we need to find the closed loop gain, output voltage, load current and output current I0 from this circuit. So I have already mentioned whenever one terminal of the op amp is connected to particular source means the same is reflected to the other terminal. So this point also will appear across node A here due to the virtual ground concept. So I can write VA as well as VB as well as Vin equal to 0.8 volts. Why? Because both the inverting and non-inverting terminals are at 0.8 volts source. Okay. And next I can calculate I1 current which is flowing through R1 and RF here. From output to input it is flowing. So that is VA by R1 here. VA value is 0.8 divided by R1 is 10 kilo ohms and the value of it is 80 microamperes. I1 current is 80 microamperes. So the same current also is flows through the RF. Why? Because the current inside the operational amplifier is 0. So first parameter we need to calculate here it is the closed loop gain ACL, that is 1 plus RF by R1, though it is non-inverting amplifier. 1 plus RF value is 20, R1 value is 10. Both are in kilo ohms and it is 3. Closed loop gain value is 3. And the second parameter we need to calculate is output voltage. So output voltage is closed loop gain times the input signal. So closed loop gain is 3 and the input voltage is 0.8 volts. So it is 2.4 volts. Output voltage is 2.4 volts. And the next parameter we need to calculate here it is load current which is flows through the load resistance RL, V0 by R. So V0 value just now we have calculated 2.4, load resistance given it as 2 kilo ohms. So it is 1.2 milliamperes. The load current value is 1.2 milliamps. And to find the output current I0, apply KCL at output node of the circuit. That is nothing but the load current is flowing in this direction and the output current will flow in this direction. Okay, so I0 current is flowing towards the circuit and these two are leaving from the circuit. So I0 equal to I1 plus IN. So I'm writing here I0 equal to I1 plus I. So I1 value is 80 microamperes and the load current is 1.2 milliamperes. So it is 1.28 milliamperes. I0 current is 1.28 milliamperes. So it is flows from output of op amp to the towards the inside the circuit of the operational amplifier. So in this way we have to calculate the parameters of the non-inverting operational amplifier from the given circuit. So in this session we discuss the problems related to the comparator circuit, AC amplifier circuit, non-inverting amplifier as well as inverting amplifier of the operational amplifier. So these all are the practical applications of the operational amplifier and their related problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.